Mr. Tarrou. In this video, we're going to start a little bit of a mini-series here. Our first video is going to be 5 examples involving the distributive property involving variable exponents. And ultimately, we're going to be moving into reviewing some advanced examples where we're factoring. But these problems, with the variable showing up in the exponent as opposed to what we may be used to in our textbooks where it's the base, it takes, depending on where you're algebraically, complicated or kind of a simple idea and really makes it a lot more complicated than it seems to be for students. It's kind of like a relatively easy problem hidden in some clothing that makes it look really confusing and complicated. And we're going to try and make sure to you it doesn't seem so complicated. Well, if we're going to be talking about multiplying bases together with any kind of exponent, whether they're variables or constants, we need to remind ourselves of what our properties of exponents are. And the two that we're going to be dealing with, actually the one in this video and the other one with an upcoming video, dealing with a lot, is the fact that when you multiply like bases that, or factors together that have the same base, what you do with those exponents is that you add them. So x to the a power times x to the b power is going to be x to the a plus b. When you divide two factors, if you will, or two items that have the same base, you're going to subtract those exponents. So x to the a power divided by x to the b power is going to be x to the a minus b. And we won't be dealing with this either in this video, but coming up in our little series it will. If you have a base that has some exponent to it, and then that itself is raised to another exponent, then what you're going to do is that sort of power property where you can bring the b down and say that it's x raised to the b times a power. So we're going to be focusing with this video mostly on this first property of exponents. So, getting to our first example, we have 5 raised to the power of x times 5, again raised to the power of x, plus 3. So we have this factor of 5 that is touching the parentheses, indicating that there is a multiplication here. And we're just going to take that monomial that's in front of this parentheses and multiply it to each of the two terms of our, well, I'm saying binomial and monomial, but a polynomial has to have exponents which are positive integers. But we're going to take this 5x and multiply it through to the 5 raised to the x power plus 3. Well, we first have here 5 to the x power times the, and let me go ahead and do this. We're going to take this 5 raised to the power of x and multiply it through the parentheses, as I just said. But I'm going to color code this for you, where we're going to make 5 to the x, that factor that we're multiplying in, we're going to make that red. So we have a 5 to the x power times 5 to the x that we're multiplying in through the parentheses. And then we have a plus 3 times 5 to the x power. Okay, well here in our first term, we're multiplying two bases together that have the same exponent. So this 5 to the x times 5 to the x power is going to become 5 to the x plus x. And with our second term, nothing's really going to happen. We're just going to have that 3 times 5 to the x. And you can write it as 3.5 to the x power, or if you like better, 3 parentheses 5 to the x. So these are equivalent. And now, of course, we have 5 raised to an exponent, which is x plus x. We're just adding like terms. X plus x is equal to 2x. And our final answer is, well, that's an awfully big 5, which looks like a 2. We have a 5 raised to the 2x power plus 3 times 5 to the x. I generally write it like that. And that is the end of our first example. So moving on to our second example. And you'll have timestamps in the description if you want to jump ahead to any of the other 4, and links to my other videos involving the distributive property. This is probably the most advanced lesson I have for this particular section, this concept to date. So we have 2 raised to the negative x power getting multiplied to this two-term expression of 2 to the x power plus 7. So we're going to distribute this 2 to the negative x. And you can write that if you want. I'm not going to, as 1 over 2 to the x, or 1/2 to the x power. Those are all three equivalent, or those two blue expressions are equivalent to 2 raised to the negative x power. But we're going to leave it the way it is and color code this again. White term, the white factor being what's in the parentheses. So we have 2 raised to the x power, and then that's times 2 to the negative x power. Then we have a plus 7 times 2 to the negative x. For students that make some sign errors more often than they should, and I make my own number of small mistakes that I'd prefer not to, but I just can't seem to help not doing, I like to write what I multiply in through the parentheses if I'm showing every single step after the terms that are inside that parentheses, and that helps with the signs that we have here with that plus 7. So again, when you multiply like bases, you add those exponents. So we have here 2 raised to the x plus negative x power, if you're just showing every single step. And then we have 7 times x to 2 raised to the negative x power. We're going to go ahead and add that x plus negative x, or x minus x, which is 0. Now to write this in a nice cleaned up version, anything to the 0 power is equal to 1. 2 to the 0 power is 1. And then plus, we have a base of 2 that is having applied to it a negative exponent. So if I want to write that negative exponent as a positive exponent, I can move the base down into the denominator, and we have 1 plus 7 over 2 to the x power. And if you haven't been shown this, the reason why anything to a 0 power is 1 is really stemming from the idea that anything divided by itself is 1, and this property of exponents where when you divide like bases, you subtract the exponents. Anything divided by itself is equal to 1, even if it's 2 raised to the x power over 2 to the x power. Anything divided by itself is equal to 1. Well, if I were to work this out differently and say, hey, you know, I'm dividing like bases, let's subtract those exponents. That's 2 to the x minus x, which is 2 to the 0, which is equal to 1. So this isn't a proof per se, but a little bit of using properties of exponents to show you how anything to the 0 power is equal to 1. And we can use the same property of exponents with division to explain how moving the base changes that exponent from a negative value to a positive one, even though you're watching a semi-advanced video here about distributive property and variable exponents, just in case no one showed you this yet. Again, the idea of giving you an example here, we have x, let's say squared over x to the 5th. That's going to become x to the 2 minus 5, or x to the negative 3rd. Well, another way of working that out, if you're really struggling with exponents, is to say that you have x squared in the numerator and x to the 5th in the denominator. Again, anything divided by itself is equal to 1, yielding you as a final answer 1 over x to the 3rd. So when we have that base with the negative exponent, if we let that base with the negative exponent move from, say, the numerator to the denominator, that's going to change the sign of that exponent. And it works if you have a negative exponent and you want to move that base up into the numerator. With our third example, just more of the same, only we're starting to introduce small steps of increase in complexity with a power now that is a fraction, which means basically in rational exponent form we're dealing with radicals. We're going to take this factor of x to the negative 1/2, multiply it through the parentheses, and we're going to have that 3x squared multiplied by x to the negative 1/2 power. We have the minus x times x to the negative 1/2, and then we have a plus 7x to the 1/2, again times x to the negative 1/2. And anytime you're multiplying like bases, you add those exponents. So we have here this 2, so that we have a common denominator of 2 instead of 2 over 1. We're going to multiply the top and bottom by 2 and write that 2 as 4 over 2. And we're going to have 3, and I'm just going to write the answer now instead of showing the middle step. We have 3 times x. We're going to add those exponents, and 4 over 2 plus negative 1 over 2 is going to yield us with 3 over 2. And then we have negative 1, okay, we have x, negative x, because negative to positive is negative. And we have 1 plus negative 1/2, or 1 minus 1/2 is just simply 1/2. And here we have plus 7, and we have this base of x, and we have 1/2 plus a negative 1/2, or 1/2 minus 1/2, which is going to be x to the 0 power. Okay, so what do we have here? We can write our final answer as 3 times x to the 3/2 power minus x to the 1/2 plus simply 7, because x to the 0 power is 1. And that's perfectly fine. If you want to reduce this fraction because you have a greater power than you have a root, so this could be rewritten and simplified as 3 times x to the 2 over 2 times x to the 1 over 2 minus x to the 1/2 power plus 7, and write our final answer as 3 times the absolute value of x times x to the 1/2 minus x to the 1/2 plus 7. Now, you may be wondering where the absolute value came from. Well, that is because of this x being raised to an even power and an even root. So if we have the square root of x squared, the even power of 2, and the even root, the square root, they're going to act as absolute value functions. And you need to include this absolute value around your variable of x anytime the directions don't say, assume that x is greater than or possibly greater than or equal to 0. And just for a little justification, if you take like a negative 3 and you square it, you get 9. If you then take the square root of 9, you get back to a positive 3, looking for the principal root, not both sort of like there's a plus or minus 3. We started with negative 3, we squared it, we square rooted, we got to positive 3. So that even power of 2 and the even root with the square root, the index of 2, acting as an absolute value function. So either one of these would be acceptable. And actually, the book that I'm teaching out of next year has this as our final answer. But if you want to do a little review about that even power of 2 and even root of 2, this could also be a form of your final answer. We've got 2 more examples coming up right now. All right, for our last 2 examples, we have got 3 raised to the power of x plus 2 times 3 raised to the power of x plus 4. And with our distributive property, I never use the acronym of FOIL because it just fails when you have more than 2 terms in one of your factors. We're going to take and make sure that each factor of each term of the first factor gets multiplied to each term of the second factor, and then move to the next term of the first factor and make sure that it gets connected to and multiplied to every term of the, in this case, second factor. And I'll go ahead and show like every single step here. Again, we have 3 raised to the x times 3 raised to the x. And then we have a plus 4 times 3 raised to the x. Now moving on to, so this 3x has been connected to each of the terms in our second factor. Moving on to the 2, we have 2 times 3 to the x. In my personal preference, I always use a dot right in the middle of that horizontal line, so it doesn't look like a decimal, and it doesn't look like just 43 raised to the power of x. And then we have a plus 2 times 4, which is going to be plus 8. Okay, so as we bring this together, in our first term here, we have 3 raised to the x times 3 raised to the x. So we're multiplying like bases. And it's a little funny because we can see the numerical value of the base and the variable is in the exponent. We're used to maybe something more like x squared times x squared, where we go, well, that's x to the 2 plus 2, which is equal to x to the 4th. That's how you usually see the distributive property and working with the properties of exponents in, well, most of my math books in the US. But here we're having, it's the same property, same process, just looks a little funny because we can see the base. But when we multiply like bases, we add those exponents. And here in our two middle terms, these are like terms. Both of these terms have a factor of 3 raised to the x powered. I'm not sure how much the blue is looking different than the white. But what you're going to do then as you add these like terms is just add those coefficients that are in front of this common factor of 3 raised to the x power. Here we have a coefficient of positive 4, and here we have a coefficient of positive 2. Do not be tempted here to say 3 times 3 is 9, nor do not be tempted as you add these like terms to do 3 plus 3 is equal to 6. Those are common errors when you're not used to seeing the base and instead having the variable as the exponent. So we're going to do 2 plus 4, which is equal to 6. And let me just go ahead and keep that coefficient highlighted. And we have that 4 plus 2 one more time is equal to 6. And we have that 3 6 times, that 3 raised to the x power, and then plus 8. And really this is, well, almost, x plus x is 2x. So we have 3 to the 2x power plus 6 times 3 to the x plus 8. This kind of problem shows up a couple of times in, say, the pre-calculus book I teach out of, but really literally just a couple of times. I don't remember in my older, it's been a long time since I taught Algebra 1 and Algebra 2, but in the States, the US, I don't remember ever seeing any problems really, or hardly any, at least doesn't come to my memory, where we have this idea of factoring where we can see the common base and instead have exponents where it's like a 2x, a 1x, and a 0. This is a pattern of quadratic equation that we see a lot of in IB and maybe wherever you go to school internationally, at least internationally in reference to the US, that I'm starting to see more and more out of the books I teach out of now. So we're building up into recognizing this in a couple of videos from now as a quadratic, a pattern for a quadratic. And how do you factor that? It's the same as factoring as always, just simple quadratics. It's just that it does look different and require a little bit of extra skill of identifying the coefficients and then identifying that these bases of 3 are not coefficients, but indeed that base, normally a base of x when we're dealing with introductory to factoring and dealing with factoring quadratics. Our last example here, we have 4 raised to the power of x minus 4 to the negative x power times itself. So we effectively have like a this binomial or two-term expression being squared. I need to stop calling it a monomial because who knows, maybe that x can represent anything and it may not be an integer, a positive integer. So multiplying this together, again, we're making sure that each term of the first factor gets connected with multiplication to each term of the second factor. And we have 4 to the x power times 4 to the x power is going to be 4, and we're adding those exponents as we go because we have the same base of 4 in each of these what's going to be factors. So we have 4 to the 2x power because x plus x is 2x. And then we have 4 to the x times negative 4 to the negative x. So what we really have here is we're multiplying like bases. So a positive times a negative is negative. We have 4 to the x times 4 to the negative x. So when we multiply those like bases, this time I'm going to show it, we're going to add those exponents. And now moving on to the next multiplication, we have a negative 4 to the negative x times positive 4 to the positive x, which is going to be negative times positive is negative. We have 4. We're multiplying these like bases together, so we're going to add those exponents. And then moving on to the last multiplication, again, negative 4 times negative 4. Well, a negative times a negative is positive. We're not doing 4 times 4 is 16 because each of these 4's have exponents, and you have to work with exponents before you deal with multiplication. If you did 4 times 4 is 16, you would be multiplying before applying the exponent, which is the wrong order of operations. So we have 4 raised to the negative x plus negative x. Well, that's going to give us 4 to the 2x power minus 4 to the x minus x is 0, minus 4 again to the negative x plus x is 0, plus 4 to the negative 2x power. Well, again, we just talked about anything to the 0 power is 1. So this is 1 and this is 1. And we have 4 to the 2x minus 1 minus or plus 4 to the negative 2x power. And we're going to clean this up. I'm going to go ahead and write this base of 4 with the negative power. I'm going to move that 4 into a denominator so that we can write this exponent as a positive value. And we have 4 to the 2x plus 1 over 4 to the 2x power. And the negative 1 minus 1 is negative 2. And that is the end of our last example. And this is going to be a series of 3. We'll be dealing with more multiplication where we're dealing with variable exponents in our next video. Again, just getting a little bit more complicated as we go through the series. I'm Mr. True. Bam! Go do your homework. Nope. Let me just do one more example. I just realized as I wrote some problems inspired by the textbook I'll be teaching out of next year, I just realized that every single one of those examples had coefficients of 1 in front of our sort of visible constant base that had the variable and the exponent. So what do you do, even though this isn't like a monomial getting, or a single term getting multiplied into a multi-term expression, but if you have 2 times 3 to the 2x times 4 times 3 to the x, recognize here that we have in these two factors, within themselves factors that have the same base of 3. So we're going to handle that kind of together. And the coefficient of the factor of 3 to the 2x power is the sort of constant, if you will, or sort of simpler part of this factor of just 2. And our coefficient of 3 to the x power over here is equal to 4. We're going to multiply the 2 and the 4 together, almost really kind of using the commutative property of multiplication, which I think I'm going to do with this next line, and move together the factor of 2 and the factor of 4, and show that we're going to be doing 2 times 4, and then, maybe I should have wrote that in red, and then have our factors rearranged where we're bringing together more closely the 3 to the 2x times 3 to the x. Now the 2 times 4 is going to give us 8, and where we had that common base of 3 with the exponents that had involved variables, we're going to have 8 times 3, add those exponents up of 2x plus x, adding them because we're multiplying those like bases, and give us ultimately 8 times 3 to the 3x power. So that's how you're going to deal with those when you have coefficients in front of that constant base dealing with involving exponents that's where the variable is in the exponent. That's how you're going to deal with those. You're just going to multiply the coefficients together like normal. 4 times 2 is 8. And with that like base of 3, add those exponents and get 8 times 3 to the 3x power. Now I'm done. I'm Mr. True. Bam! Go do your homework.